We need to continue our exploration, which is moving us towards a cosmology, a cosmological debate, in fact, which is happening right now in astronomy, which is quite exciting. And our last week, which will be next week, is scheduled to be all about the Big Bang. And so we'll definitely be talking about what we haven't talked about with regards to the Big Bang. But in all honesty, we've kind of cracked open the topic at various points which are relevant so far. And we'll polish up some of the details. But today we're going to continue on that story. The questions that the textbook seems to be posing at this point are questions like, which came first, stars or galaxies? How do galaxies change over the course of their lives, if we can call them lives? It's hard to call them anything else. And so what determines what shape they have? Is there a nature versus nurture aspect to this in terms of the outcome of the particular shapes of these things and their behaviors? And all these are deeply evolutionary questions. The problem with using the word evolution to describe the shapes of galaxies and even planets is that it seems like evolution is generally a population level study, right? And it inherently is biological in that you have generation upon generation and you have the preservation of traits. This is really more of a metamorphosis, right? Where things change shape and then they get destroyed and fall apart. And there's something cyclic about it, just like we talked about with stars. They live, they die, and when they die, they give off components that allow us to build more stars as a result of it. So I think we'll try to stick to the concept of metamorphosis instead of evolution, because I think it's a little more appropriate. But in general, we're entering into the absolute bleeding edge of what's known, right? We have gone far beyond our immediate direct observations, and we're starting to make assumptions about the bodies at great distances, about the bright features in the sky that are very far away, and we're using those to calculate additional features of our theory. And so any of our uncertainties that we encounter are compounding over time, and this makes things very squishy, and that's why we're entering into this very difficult terrain now, where we can't say a lot of things with certainty, and in fact, we've encountered a great deal of difficulty and conflict in terms of the conclusions that we're making, which is why our cosmology is somewhat on the ropes right now, and I think that's very exciting. I don't mean that in a derogatory sense. I mean that in terms of us being able to really update our understanding in a giant quantum leap very soon. I think that is on the table. So I want to be very clear about something. I'm going to try to build this as we continue to finish out this course. I want to really focus your attention on something which is really important here. And it's particularly exemplified by the fact that we don't have a lot of facts at this level of our discussion, right? We're making hypothetical explanations for what we see, and there's a lot of missing pieces. And so I think that a huge part of the reason why you guys are all here in college in the first place, I hope, is that you're here to practice and learn the art of how to think and solve problems. You're not here to learn what to think so much as you're here to learn how to think. And I believe that that's the way forward in terms of all of these topics that we're going to explore, and we've been exploring. And so as I draw your attention to some of the holes in our understanding, I don't want you to think that I'm trying to be overly critical of our knowledge base. I'm trying to give you guys a sense of how to approach something like our understanding of the universe. But how about our understanding of anything? It's very important to approach it with an eye for what's missing in the story. And I think this is something that you can apply to whatever your particular field of interest is. If your goal is to write short stories, you need to appraise your stories with the same mindset of what's missing here, right? And so we're going to keep pursuing that method as we go through these different topics. Now, before I can continue with the textbook per se, I do want to wrap up a few points about the active galactic nuclei. I also am going to move into speaking about how galaxies potentially interact with one another a bit more, so merging and the chaotic processes that result, because it seems like those probably play into the form and features of galaxies more than we thought originally. And then finally, we'll wrap up with the cosmological principle, which is at the heart of our cosmology today, and seems to be one of the biggest problems with our cosmology. And this threatens, in some sense, our ability to make conclusions about very distant things, because the cosmological principle, which I'll elaborate on in a moment, comes down to the assumption that everything in the universe is more or less the same everywhere. And that's a gross oversimplification, but I think that it is at the heart of the conclusions that we've made to some extent. So we'll get into the cosmological principle at the very end here, because the cosmological principle is what we're going to use to build out the standard cosmology, and it's the same principle that we're going to use to imagine what the next generation cosmology might look like. And I think that that's what we should really be focusing on as young people looking at the world of the future. Okay, before we do that, I do want to wrap up a little bit because I got cut off at the end of class last time. And some people had some questions about those things after class last time, and some people emailed me. We talked about these active galactic nuclei and quasars, and we talked about the standard model for what is happening, which of course involves black holes, which is a place where physics is proposed to break down completely. You know, and somebody asked me what that means exactly. What does an infinity mean? What does it mean for physics to break down? Well, it means that the mathematical model which describes what happens during gravitation, which we use general relativity, it's very, very precise in terms of our local measurements of it. Well, when you have too much stuff in one place, or you have so much gravitation that you think you have so much stuff in one place, then at some point, the forces of that gravity are so high, they actually reach to infinity. And you find a point following these models where you have a point of infinite density in zero volume. This is called a singularity. Now, this is essentially what a black hole is a placeholder for, is the moment where our understanding of gravitational physics breaks down. And I think it's really important to understand that when we've seen singularities in the past in science, unanimously, those infinities turn out to reveal some really exciting feature of physical reality that we didn't understand previously. And so there's two very good examples of that I want to remind you of. And I think I've brought them up before, but I think that they bear repeating. So there's two very famous infinities that turned out to completely rewrite how we understood nature. The first one was the question of heat, okay? So in the beginning of rational science, the beginning of the Enlightenment, when people started to first propose the idea that there was an alternative to superstition, that we could actually explain cause and effect in a mechanistic sense, we developed equations that allowed us to build engines, shortly thereafter, steam engines mostly. And the equations that featured, that instructed us on how to, and detailed the process of how engines worked, gave us the basic science of thermodynamics. Now, thermodynamics was based on the idea that heat flowed from one body to another, and there was certain conservation principles that restricted that flow. So naturally, everyone at the time, for 100+ years, hundreds of years, let's say, assumed that heat was a fluid which flowed from one body to the next. Now, this turns out to work perfectly, actually. It's a perfect mathematical description of how heat behaves. It flows from one body to the next. The problem was that this fluid was a very dark fluid. It was mysterious, and it didn't behave like other fluids, and we couldn't detect it exactly. What do I mean by that? Well, heat as a fluid turns out to give us a situation where we can produce infinite quantities of it by grinding one object against another. And this was discovered during the process of producing cannons during the Napoleonic era. People were boring out, using these drills to grind the cannon bores, the barrels of them out, right? And they noticed that no matter if they kept grinding and kept grinding and kept grinding, they were able to produce more and more and more heat. It didn't seem like heat could be exhausted. And so experimentalists were troubled by this because it seemed like this fluid would infinitely produce itself, no matter how much you kept doing it, right? And this was a tremendous problem because, again, infinite production of some fluid, some magical fluid, is inconceivable. Now, there were people at the time who argued, well, that's just how it is. Physics breaks down. This is a special case scenario where things don't make sense and that's okay. We should move on. The equations work perfectly. It took somebody to come along and build another bridge next to it, and that bridge was called the kinetic theory of gases. And what it was, this was particularly the work of Ludwig Boltzmann, they proposed that actually what was happening during the production of heat was that the atoms, the material actors involved, were just vibrating at different modes. They were more excited, and that's what actually led to the production of heat. So it was a motion of some regular body that produced the heat. Therefore, if you supplied a motion in the form of a drill, you could endlessly produce more motion in the form of heat. And this actually removed the infinities from the equation. But it didn't change the math. We still use parallel ideas. Now, we've introduced some scaling constants, right? We've actually introduced a quantization of that, which is the molecular unit of motion, which is captured in the Boltzmann constant, which if you get into scientific theory, you see that everywhere. But we understand that it is individual molecules that are actually moving and producing this heat. Another one, which I've talked about before, is the ultraviolet catastrophe, which was people trying to understand why, as you went into higher and higher frequencies, you didn't produce infinite quantities of energy. And this was an easy one to see because people did black body spectrums, and they could see that when you heated things up, you actually didn't produce infinite quantities of energy down in the short wavelength regions. Again, this was solved because a very brilliant gentleman came along. This was Max Planck, and he said, you know what? I can actually make this infinity go away if I assume, like the kinetic theory of gases, that there's an individual unit of light, which we now call the photon. So we now understand that light occurs in packets, right? There's little bursts that are discrete. And this, again, took the infinity out of the equation, and science took a giant leap forward. I'm telling you all this because we're facing some really crazy infinities in astronomy and astrophysics right now. The black hole is an infinity. This is a problem that needs to be solved. The concept of the birth of the universe contains an infinity. This is another problem that needs to be solved. And so I don't think that we should just put our pens down and accept these infinities as real features of nature. I think they are there to tell us that we don't understand how something is working perfectly. All right. There's a couple more points I want to make. The history of astronomy also tells us a couple of really interesting things. One, everything tends to be further away than we think it is, right? You think back just to the early 20th century, everyone believed that the entire universe was the size of the Milky Way, and there was a great multi-decade debate about whether there was anything beyond our Milky Way, whether these nebula that people were examining with these strange spectral features could perhaps be outside of our galaxy. Well, it turns out that, of course, we now can see them with great telescopes, and they look just like our galaxy in some sense, and they look like different types of galaxies. We understand they're galaxies that are very, very far away. So we need to keep that in mind as well as we go into this discussion about the edge of what we can see, which turns out to be about somewhere in the neighborhood of 14 billion light years away, right? Which, yes?
What do you think about the idea that the universe is neither infinite nor has an edge, but is actually the surface of a four-dimensional sphere, in the sense that you could go in the same direction forever and eventually end up back at the same spot?
We will play with that more next week. Okay. Yeah. So the question is, what is the shape of space? We'll play with that in a little bit. Yeah, we'll get back to that, I promise. The second thing I want to point out to you is that historically speaking, everything is always older than we thought it was. So at the beginning of the Enlightenment, almost everyone assumed that the Earth was actually only several thousands of years old, actually. And all the way up into the 20th century, one of the most popular theories of the day was this dude, Lord Kelvin's idea about the formation of the planets and so forth, and we talked about this briefly. Lord Kelvin had calculated that the age of the Earth was about 20 million years at most, okay? Today, the oldest rocks that we can date back to billions of years, let's say, 4 billion years perhaps. And so this is our expanded understanding of how old the place is. Now, does that mean that that's as old as the Earth is? Well, that means that's as old as the last time the place got cooked, at least. That's the last time radioactive elements were incorporated into the rocks. But in general, we are moving the goalpost, and we keep moving it. And I think that that's something we have to consider, too, when we talk about something like the age of the universe. Well, that's our as far as we can see, and that's our best estimate of what we can say, really. That's as far as we can say that things are, okay? But I think that will change, and I think that history has shown that that continues to change. Another thing to point out is that we often confuse two phenomena for the same thing. The history of variable stars and using those as standard candles to gauge distance proved this out, right? Originally, we thought that Cepheid variables, which we could use as standard candles, were all the same everywhere. It turns out that the ones that we were using as our standard candles in the 20th century turned out to actually be two different types of Cepheid variables. And this ended up expanding our distance measurements by 2x very quickly, like that, overnight, when people figured this out. So things are more complicated than we generally give them credit for until we are able to really integrate new pieces of information. And then finally, whenever you see this word dark or black in a scientific theory, it almost always means that we're missing something and we don't know how to explain this, so we're putting a placeholder there until we get around to figuring it out. Now, you put all four of those ideas in line, they should give you an idea of what's coming next, because there are some very obvious topics here that we're going to be moving through, and we have moved through some of them, that certainly have explanations that require some deep thought and reconsideration of our basic principles. So again, like we were talking about in our conversation about mythology, if there's a dragon in the room, you gotta slay that dragon, right? You can't just pretend like it's not a problem. It's gonna absolutely rule your roost otherwise. And the great thing about science, if there's anything great about science in its idealized form, is that it allows the individual, each one of you, to understand how something works and then work off of that understanding. You don't have to take someone's word for it. That's the best case scenario for science. And that's very much in opposition to what came before science, which was this idea that, some priest told you how things are and you go with it, or you get burned at the stake. So those are your two options. Now, of course, science, there's plenty of priest-like people working in science who would definitely burn you at the stake for not going with what they say, but that's not an idealized form. That's just an inherent corruption that happens, right? Power structures do tend to corrupt, and there are places where things break down. But ideally speaking, your understanding by looking at theory and listening to the explanation should allow you to decide whether you agree with it or not, and whether it makes sense to you or not. It's totally up to you at the end of the day, which is something kind of amazing. So don't ignore dragons. There's a lot of work to be done. Questions? Okay. I did want to briefly follow up on the galactic magnetic fields because I got a little bit cut off at the end there. Why does your textbook not deal with galactic magnetic fields? Well, it's a brand new field of inquiry, not because we haven't noticed that galaxies have magnetic activity, but the magnetic fields are chaotic. They're not organized in a way that lends themselves to direct perception. If you look far away at the magnetic field overall of a galaxy, you'll find it's extremely weak. It's actually much weaker than the Earth's magnetic field. However, if you look at the local structures, and this is where the cutting-edge work is going on right now, if you look at, say, the magnetic field of the individual arms, right, or the individual star systems in some cluster, they're quite coherent, and they sum up to actually quite powerful interactions, or quite powerful forces that can play out. And I think that we'll be seeing more of that in the future in terms of explaining these questions that we're trying to crack open, like why do galaxies look the way they do? What is happening with these active galactic nuclei? How do they focus these tight beams, right? Okay. Questions about the magnetic fields? All right. So back to the textbook a little bit. Let's continue with this narrative. So the standard narrative here is something like we have various techniques to look into the distance. We assume that distance is related to the past, and we can make theories about how things change over time as a result of that. And there's a few different techniques that we use to do that, and we've gone through a number of those. And it doesn't work, obviously, to just stare at a galaxy and see how it changes with time, because these things happen on the order of millions and billions of years, right? In fact, we're going to talk a little bit about galactic mergers. We mentioned it briefly before, but of course Andromeda, our nearest spiral galaxy, is coming straight at us, and it should be here any day now. No, it's not going to be here for like 4.5 billion more years, right? So that's going to be a while. None of us are going to be here to see that. And actually, the interaction that's going to take place isn't probably what you would expect, because there's an unbelievable amount of void in between the star systems. It's unlikely that any of the stars are even going to crash into each other. That's how far apart all of these things are. But there will be interactions, and they will probably shape the galaxy moving forward. So the basic premise that the textbook takes, if we can see thousands of these galaxies at billions of years away, and we assume that billions of years ago there was a birth of everything, then those will teach us about how young galaxies should turn into older galaxies, like the ones that are close to us. Now, this is all very reasonable, but it is pinned on the assumption that the things you're seeing 14 billion light years away are the earliest features of the universe. But this is confounded by the fact that we can only see 14 billion light years away. And so it's something of an untestable hypothesis, in that we don't really have the ability to say whether there's something that's 14 more billion light years away and we can't see it because that's the edge of our detection, or whether that really is the first stuff that appeared here in this world that we find ourselves in. So I think there's a little grain of, maybe a large grain of, maybe a cup of salt to be taken with statements and so, like this. So this is a quote from your textbook. This cosmic time machine then lets us peer into the past to answer fundamental questions about where galaxies come from and how they got to be where they are today. That may be true. It may be absolutely untrue. It's very difficult to say. But I will point out to you that I can't figure this out either. At some places in your textbook mention the James Webb telescope. This chapter does not, which is very strange. Because, of course, if any of you are nerding out on the science headlines these days, you probably see something that looks like this. Galaxies shockingly similar to our own found near the beginning of the universe. So, for better or for worse, the textbook follows this narrative that if we look at these early galaxies, if we look at these distant galaxies, they should be early, they should be less developed, and we can learn about how things develop from something simple into something complex like our own galaxy. But this is a tenuous assertion at this point, especially with the new James Webb data. Actually, we're seeing fully formed spiral galaxies within, I don't want to say moments, but within a few 100 million years after this supposed moment of inception of this universe. And this is an almost impossible feature to explain with the existing cosmology that we have today. So I think they were on the verge of turning a page to a new way of looking at these things. Now, I don't know if the page turn will result in us conceiving of a galaxy that's just older, a universe that's just older, or if we will consider the fact again, like we did prior to the 1960s and 70s, that perhaps the universe has no age whatsoever. Perhaps it's always been here, which is a really interesting proposal. And, from a mechanistic standpoint, science is always trying to give us a cause for the effects that we see. It's much easier to explain. If you want to propose the universe has a beginning, well, then you have to supply a cause for that effect, which is an extremely difficult thing to do because let's say the universe means, in this context, the universe means everything that exists and everything that's happening. Well, how do you give a first cause for everything to exist and everything to happen? Well, you find yourself very much outside of the realm of science at that point because you can't really supply a mechanistic cause for that. And so in some sense, the default is that there is no event. There is no start. Because you don't need a cause to explain that. It just is so, right? So, and it's worth pointing out, again, I know I've mentioned it before, but prior to the 1960s and 70s, this was actually the more popular opinion. It only took the discovery of the CMB to win over most astrophysicists to the idea that, okay, this must be the echo of this big bang, this event that happened in the distant past. But there's some issues with that popping up too. And I'm going to try to spend maybe a quarter of our time next week on the CMB because it's a very, very nuanced topic and we need to look at it with the luxury of depth. So let's keep going here. Let's give some stage time to the idea that we are looking into the early moments of the universe, because I think this is at least the paradigm that we're moving from into something new. We should understand it very well so that we can learn something about where we go next. So it's worth pointing out, remember the distance ladder. Our most precise and direct measurements of distance come from very near bodies, right? The moon, the sun, the planets, where we can make parallax estimates. We can see exactly how far away these things are by some simple geometry. As we get further and further away, we have to depend on our theories about what those bodies are doing in order to make our distance estimates. And at this point, especially at the distances that we're going to be talking about today, the distance of a galaxy is derived almost exclusively from its redshift. And this redshift is a very, it's a very, what's the word? It's very pernicious. It's a very tricky and potentially dastardly inference, because if the redshift has anything to do with anything other than recession velocity, then our theories are in deep water. So we have to take these distances with a grain of salt. There's a pretty serious degree of uncertainty about these. And at any rate, we use the rate of recession to calculate this thing we call the Hubble constant, which we mentioned before, which tells us how this expansion is occurring and how it's actually accelerating at some point. Now, by the way, our standard cosmology is called lambda CDM, and I didn't explain this to you before. The lambda is actually the term for the Hubble constant. This is the expansion properties, the rate of expansion. The CDM stands for cold dark matter. So it turns out that when we try to calculate based on the attractive behaviors of different bodies to one another, when we try to calculate how much gravity should be at play, assuming gravity is the only player here, we calculate that that something like 4% of the gravity is due to bodies that we can see. That means that the overwhelming majority of the material that's supposed to be there isn't visible. We can't see it. It doesn't have a thermal signature, and we can't see it with our ordinary electromagnetic probes. It doesn't give off light, doesn't interact with light. So something weird is going on there. So we call this stuff cold, dark matter, right? Now, is there something there? Maybe. But if it's there, it's very, very cold, right? So could the universe be populated by all sorts of old, dead star remains that are just freezing and unavailable and not scattering light, and we can't see them? Perhaps. Perhaps interstellar space, intergalactic space is just crowded with all sorts of debris from long-gone galaxies. But of course, if that were the case, it would take far longer than this 14 billion years that we have constrained our ideas about the universe to. So that's a feature that we could see coming out later. You know, to me, it seems like it's possible that if we move our date back for the birth of the universe, which seems very likely, or if we get rid of it altogether, then we have a tremendous amount of time in order to accumulate cold stuff. So maybe dark matter turns out to be ordinary matter that's extremely cold and dispersed. Or maybe we don't understand something fundamental about how atoms work. Maybe there's something else at play here in the universe that we just don't grasp, some exotic form of matter. But we'll see. So, you know, all of our dynamics depend on this. We've talked about how the rotation of the galaxy doesn't appear to be gravitational unless we stick, you know, 90%, let's say, hundreds, thousands of times the amount, nearly 1,000 times the amount of material that's in the galaxy outside of the galaxy around it that we just don't see. Well, then we can describe the rotation of the galaxy in gravitational terms. But this is a compounding error in that we assume that galaxies' rotation is due to their mass, and then we look at the rotation of galaxies far away, and we deduce their mass based on their rotation. So this is a very circular reasoning in some sense. And I'm not telling you this stuff in order to kick the machine and tell you that these people are morons or anything. I think that we're doing the absolute correct thing by putting placeholders in because we don't understand how these things work, and we need to move forward, and we need to compile our understanding into something that is cohesive. But we absolutely can't pretend like there aren't dragons in the room because these absolutely need to be addressed. And I think they are to some extent. We'll get more into that next week and look at some of the alternative proposals, which I think are quite exciting. So anyways, let's go back to this assumption that the distances tell us about the early years. Well, it seems like if we look to these early years, if we look far, far away, we see galaxies that are bluer. And I don't mean their overall spectrum. I mean that their individual populations of stars seem to be bluer. They're all redshifted, of course, but the blue stars, remember, redshift refers to all of the frequencies being tilted towards the red. But there's still going to be blue populations within that and red populations within that. And the red ones are, of course, the older stars, according to our model of stellar metamorphosis. The blue ones are going to be the newer ones. And actually, we see more of these bluer ones, which reinforces this idea that they're younger. Now, God only knows what happens to light as it travels 14 billion years across the cosmos, right? So there's a lot of features that could lead to the reddening, which we don't have good models for because there's no way to study those kind of enormous distances here on Earth. It's very, very tricky to imagine how one would do that. You know, if you think about something like a sound wave, right? If you, let me think of a good example for this. Have you guys ever walked up on a marching band before? Anybody? You notice that the first thing you hear when you walk up on a marching band are the low frequencies, actually. Think of another example. Well, somebody was doing some, like, I don't know if it was the ROTC or what, but somebody was doing some very loud, like, athletic drills this morning when I came onto campus. You heard that too? I was like, what is that? But you hear people, right? Really low frequencies first, right? Now, that's because of the fact that when waves of energy in air, so collisions and deformation of, say, the material in the walls that are keeping that sound inside, well, what happens is that those sound waves are losing energy across the distance that they're traveling because as each collision happens, a little bit of energy is lost to heat, to friction. Now, there's not really been a successful theory to explain how this happens in terms of light because the only way that we can conceive of light losing energy is through scattering. That's when it's redirected into a new, by a new trajectory. But it's very likely that the reason that we don't understand whether or not, and I would say we don't understand how light loses energy, is because we don't really have a material conception of how light works. We don't really understand how light is relayed from one atom to another, particularly with neutral atoms, where we would say light just doesn't interact with them whatsoever. It just magically goes right through those atoms. Well, I sincerely doubt that it doesn't interact with them. I think it might not be redirected, it might not scatter, it might not be repolarized, but something probably happens. There's some sort of transaction which occurs. And if you think about billions and billions of light years of light traveling and interacting with atoms all along the way, well, there's probably some energy losses. And somebody is probably going to figure out how that works sooner or later. And that's going to probably at least add a new component to this concept of redshift and how this happens. And so that's definitely something to look forward to. And I know a number of people who are working on that problem very diligently. Okay. So I said so again. I'm going to try to stop doing that. Come on. Another important clue that we need to look at is the shape of galaxies, because we're trying to understand how they form. And of course, the formation process takes billions of years, and we don't really know, we don't have a lot to say about that unless we assume that the things that are far away are very young, and we can make some sort of metamorphic conclusions about that. Now, obviously, we have some very clear bins of galaxies. We have the spiral galaxies. We have these just ball elliptical galaxies. We have galaxies with bars and some that don't have bars. And there's some features about those which are kind of interesting. So spiral galaxies seem to contain young stars and a lot of interstellar material, just gas and different ionized atoms. Elliptical galaxies have mostly old stars and almost no new star formation. So it's probably a reasonable conclusion to assume that they're older, which is interesting because they're sort of more chaotic looking. So they've probably been around the block a few times, which is, I think, a fair conclusion. Now, we can do some counts, and we can try to count up how many of each type we see at different distances. And what we see is that all galaxies contain some degree of old stars. You know, our own galaxy contains a lot of old stars, but it has this organization that tends towards suggesting that it's newer, right? It's not sort of devolved into this elliptical form yet. So it seems like at least some of our stars formed very, very long time ago. And I mean as long and as old as anything we can see. Just a few, I keep wanting to say moments, but a few cosmological moments after the proposed inception of the universe, which is very strange. So we have stars in our own galaxy that have been around this whole time. And so when we look at these elliptical galaxies that are full of these stars, we think, well, they also have some of these really, really old stars. They must not have changed very much over this period. And we'll get back to that later. When we look at the observations of quasars and the active galactic nuclei, we see the same thing. There's a lot more of these in the distance, which is quite interesting. Now, of course, all of this, again, depends on the idea that what we see in the distance is reflective of what's happening here, which is a very tenuous assumption in its own right. Remember, this got us into a hole with the Cephids originally. There's something else that's worth mentioning, too. And I'd saved this kind of for the end of the lecture before, but when we talk about looking into the deep distance, a lot of people have the impression that we're looking everywhere. But in reality, we're only looking at a tiny little portion of the sky that's actually pointed away from our own galaxy, right? We can't look into, say we're in the arm of this galaxy, which is essentially a disk. There's a lot of bright stuff above and below it. Look there. So the only place we can look is a tiny little window right here. And actually, all of the Hubble measurements that we've been referring to that have given us these different redshift measurements, they refer to a tiny little window on the sky where we're able to look and see things off there. And so all of our conclusions are based on something like one person. If we wanted to say something about the human race and we were able to pluck one human out from it, and we were to try to draw a conclusion about all people as a result of that, well, what happens if you grab a psychopath, which turns out to be like 5% of the population? What happens if you, I don't know, you can just let your imagination go to work here. So you have to be very, very careful with the certainty that we pronounce about these things. I really just can't hit you over the head with this because I don't think that the textbook does a good enough job of this. The textbook kind of makes it seem like, well, we've looked everywhere and this is what it looks like everywhere. Yeah.
For like instance, through the Milky Way, we have no idea what's on the other side of it. Like,
No, there's some wavelengths that, some radio waves, but yeah, basically no. Actually, that's really interesting too when we look at the CMB, because these CMB projections, well, we'll get into this next week, but I'll actually take apart the map of the CMB for you and show you what it looked like before we subtracted out the Milky Way from it. It looked like the Milky Way. So this is a huge problem, actually, that we have to look at things through the tiny window that's available to us. And that's all well and good. I think that's really interesting to look at that. But somehow something gets lost in translation in these textbooks and in the popular media, and unfortunately in the minds of a lot of astronomers as well, where, you know, I've talked to very, very, very esteemed astronomers who had, well, many of them have thought about these things, but a few of them, I'll point some of these things out, and it's like the first time they've even been hit with it before, right? So I think it's very easy to become indoctrinated into one way of looking at things and assume that it's the entire picture. And this is why the cosmological principle is on the ropes so bad right now. Again, the point here, the point about your entire lives is to learn how to think, not what to think. If you go into astronomy and you become a very esteemed astronomer, you might be able to do that by learning what to think. That might get you pretty far, actually. Whatever you do, say you become a business owner, you might get pretty far learning what to do in your business from somebody who's done it before you. That'll get you pretty far, but it won't make you a Steve Jobs, right? It's not going to make you a Jeff Bezos, right? These are people who actually learned how to think about the problem and applied it in a new way that no one had ever thought of before. That's how the world actually moves forward, and that's really what we're trying to get at here. Okay. Now, this image here shows something which has a redshift of about 8.68, which corresponds to 13.2 billion light years. The James Webb Telescope's finding redshifts that are 16, 17. Some of them have been reported at 30, okay? Now, people in the literature they said, you know, there's a lot of contention about this. Well, maybe you haven't calibrated your measurements right, maybe something's wrong here. Or maybe there really are galaxies that are far, 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 far further off and far, far older than we've been able to incorporate into this so far. So I think this is really exciting. I hope I'm not breaking anyone's heart here, honestly. I'm not doing this to be a thorn in the side. And it's actually quite exciting that you all are here at SOU, where we don't have an astronomy department, because there's nobody who's interested in maintaining the old way of thinking, right? There's nobody who's going to fire me for talking about these. Well, they might, but somebody might. But you know, the department head here of the physics department is also very interested in these questions. You know, when I agreed to take this job, I told her that I'm not completely convinced of this Big Bang stuff. And she said, yeah, I don't know, maybe it didn't happen. I said, whoa, all right, cool. Well, we'll explore both possibilities in this class then. So here we are. All right, so again, this is our Hubble deep field, the one that I was talking about through that little peephole in the sky. Now, to get a picture like this, and this is showing these are showing the farthest that we could see. Now we have the James Webb, but it's essentially the same thing. It's a little bit higher resolution. It's got a bigger mirror, so it can see more. Now, this is actually requiring 11 days of exposure to this this field because there's so little light coming in. And this is actually in a tiny region of the sky. It's actually it's in the constellation Fornax, which is near the celestial South Pole. And we use that because it has very, very few Milky Way stars, right? It's pointed away from the Milky Way. There's very little light which is going to get in the way of our observations. So, these are textbook cases of what we would refer to as early galaxies. I think that it's probably more fair to say that they are very far away galaxies. Of course, they have extraordinary redshifts, and they're very dim for the most part. All right, I think I've said enough about that. Let's talk about galactic mergers. So this is actually one of the more interesting features that we see out in the night sky. Well, here we have these incredible rings showing up. If you look at these pictures, there's tendrils of stars and gas and sort of interesting complex structures that appear to be resulting from interactions between the different galaxies. And the details of these processes are incomplete. We obviously can't observe them happening in real time, but what they do teach us is that perhaps some of the features of even our own galaxy or the galaxies that we see are not the result of their natural unblemished progression, their natural unblemished, God, it's so hard not to say evolution, metamorphosis, but perhaps they're interacting with their environment in an interesting way, which is giving them features. Now, there's not a ton to say about that, other than the fact that what we're seeing probably has to do with interactions as much as it has to do with the aging in place. So what people try to do is the scientists try to do is they try to input the features of a galaxy, say its proposed mass, which of course includes all of this dark stuff we can't see, and they run these very elaborate computer simulations, interactions between all of these point particles that represent the different masses and so forth, and they're able to reproduce features of how these galaxies form. I'm going to turn down that light a little bit so you all can see a bit better. Now, when they do these simulations, they find that sometimes the little galaxies get completely gobbled up by the big ones, and sometimes they just pull on it in weird ways. So there's all sorts of different features that can get acquired by these interactions. The monster galaxies often have more than one nucleus, which is quite interesting. So this could be the result of these merger systems. Now that's something to think about. Can you imagine a galaxy like our own with more than one? Well, it turns out that is something that we propose is a feature of these really large bulges that we see in some of these distant galaxies. Well, maybe there are more than one galaxy sitting on top of one another, essentially. Sometimes galaxies don't change shape when these collisions happen during the simulations, which is quite interesting. Because like I said, there's so much distance in between each one of our stars that it's completely possible you could shuffle these decks of cards together and have them come out on the other side completely unscathed. However, when these processes happen, it's thought that there is a great deal of this stirring that occurs with that interstellar material, right? All of that dust and gas is getting whipped up into motion. And the thought is that as that happens, you can nucleate the birth of new stars, actually. And so perhaps galactic interactions are responsible for these bursts of star formation. Now, astronomers have a word for that. They call them starbursts, which is not the little candy. Do they still make those candies, by the way? They were very popular when I was a kid. Okay. So anyways, that's what that word means, starburst. It's actually what astronomers refer to when they see a ton of new stars in a very distant galaxy. They think there must have been a galactic merger in the recent past there. And that's kind of interesting. And here we have a couple pictures of this starburst phenomenon happening. This is a group of galaxies. This is one of my favorite pictures out there. This is called a group of galaxies called Stephan's Quintet. And they appear to be all interacting with one another. There's these long strings of young, massive blue stars. And hundreds of star-forming regions, and it's really quite an elaborate zoo of interactions. Some of these star clusters range from just a couple million years to billions of years old, so you kind of have a little bit of everything. All right. This is another interesting feature here is that when we look far away, we seem to see more of these active galactic nuclei in the distance than we see around us. So this is, of course, taken to support the idea that there was more star formation in the distant past than there is today. This is a totally reasonable conclusion if, in fact, the things that are distant are, in fact, universally older than the things that are close to us. Now, if our window is wrong, or if our ideas about redshift are incomplete, this idea might change. And actually, this is one of the most beautiful pictures of an active galactic nucleus. This is Centaurus A, which has these very beautiful jets, these blue and orange jets. And there's these huge lobes of gas, hot X-rays being emitted from these. This thing is very, very close to us, though. This is actually only 13 million light years away. Right? So that's 1,000 times closer than the galaxies that I showed you at the beginning of this lecture when I was showing you how some of the very early galaxies look very much like our own. Now, these AGNs actually, these jets, seem like they could be very important as well in shaping how a galaxy looks, right? Because what the AGNs potentially do is these jets push all of that interstellar material away, right? And you need that interstellar material in order to make new stars. So it's possible that one feature that results in the shapes of these galaxies is that these jets are clearing out all of the stuff that you'd need to make new stars, and therefore you have a sort of an area in the center, an area above and below that's cleared out, that's cleaned out. So there isn't a lot of room for this thing to be this kind of starburst super birth systems to be happening with regards to star formation. And this might play into our own galaxy a little bit too, because we don't see this AGN sort of phenomena in our own galaxy right now. But there's reason to believe it may have happened in the past, and particularly that we see these gas plumes away from the center of our own nucleus, despite the fact that there's no active massive active jets going on that are doing that. Well, perhaps they've done it in the past. All right. Ah, yes. Cosmological principle. All right, so Hubble, probably the most household name of all astronomers, I would argue, at least as long as at least when I was growing up, because the Hubble telescope was this massive feat of engineering. Maybe James Webb will be the more famous astronomer later. But I think James Webb got in trouble now. They just call it the JWST. I think he got deplatformed for some reason. I didn't follow up on that. But maybe they'll change the name of that telescope. Hubble made two discoveries that turned out to be absolutely critical for the story of the universe that we've been left with here in the textbook. First discovery that he made was that the number of galaxies visible in each area of the sky was more or less the same. Now, Hubble didn't have the Hubble telescope, right? Hubble had Earth-based telescopes, which were they very much underperformed the even predecessor to our generation of telescopes, right? So this was one point. He also found that the number of galaxies increase with faintness. And so, the conclusion from this is that the density of galaxies is essentially about the same in every direction. The overarching principle, which I introduced to you before, is that the universe is more or less the same over there as it is over here. This is the fundamental principle at the heart of the cosmology which became popular at the end of the 20th century, which is this lambda CDM, which I've been speaking about. So the fundamental conclusion from this is that because the universe is about the same anywhere, the conclusions that we draw from the things around us are essentially the ones we can draw from the things that are far away. And, you know, a quote from your book goes like this: "Without the cosmological principle, we could make no progress at all in studying the universe." Well, I think that's a bit overblown, but it shows you how much our understanding of these large-scale behaviors depends on this assumption, which is rapidly proving to not be the case, okay? So I think this is really fascinating. Now, you know, this is, we'll talk about the CMB later, but for today, it's suffice to say that CMB was almost immediately reported to reflect this afterglow of the Big Bang, right? This moment when the atoms were reconstituted and recombined for the first time, and they sent photons off in every direction, which rattled around the universe for eons and eventually gave a rather homogeneous signature. So this is the picture that's usually used to show that the CMB is quite isotropic. These are temperature variation. There are slight temperature variations, but you know, maybe they're just due to noise. These are, by the way, this red and blue, this is the heat and cold of it. They're like small percentages of the overall temperature signature, which is quite small. It's actually, I believe that it's in the 3 Kelvin range, right? This is very, very weak, cold signal. By the way, Kelvin. Room temperature is around 300 Kelvin, right? 0 means the atoms aren't moving at all. It's actually darn near impossible to make an atom stop moving. So 0 Kelvin is unachievable. These are very, very cold signatures that we're getting from this, okay? Now, this was essentially the graph which was produced as having, once this is actually done after a series of different measurements of the CMB, and we'll deal with that on Monday or Tuesday. But one of the things that they did in order to generate this graph, this isotropic graph of the CMB, was they removed the Doppler shift effects due to the redshift, right? So this is actually what the CMB looks like after you subtract the galaxy out from it, okay? So, and that's really, we'll talk about subtracting the galaxy out. It looks much, much worse than this, my friends, before you subtract the galaxy out from it. But what you see is that there's clearly a reddening and a bluing of it. And this was for a long time thought to be a result of the motion of ourselves with respect to things that were far away. Okay, this is a perfectly reasonable conclusion. So they deleted this effect. They subtracted it from the measurements in order to produce the isotropic map that you see there. However, there's 3 main problems with that. There's a problem with isotropy, there's a problem with homogeneity, and there's a problem with the CMB dipole. I think that we'll get in, the homogeneity and isotropy we'll deal with later. By the way, those 2 words, I want to make sure, well, let's deal with them later. We'll define them and break them down with more depth when we get to the CMB, because I want to spend more time on this CMB and explain to you how these maps are made. But suffice it to say that the CMB, we realize that these photons are actually polarized to some degree. There's a dipole associated with these photons. That means they have some sort of orientation. And the dipole anisotropy, so what does anisotropy mean? Anisotropy means irregularity. There's some sort of, it's not the same everywhere. In some places it's more polarized, in some places it's less polarized. Well, it's not often advertised that there is a dipole anisotropy in the CMB, and that the amplitude of that dipole exceeds the amplitudes of the other temperature fluctuations, and that's what you see in this picture here. So it's subtracted, and that's due to what we assumed was the Doppler effect, which is our relative motion with respect to it. However, in recent years, that assumption has been tested, and the current results are a little bit troubling, because they show that our motion with respect to the distant radio galaxies and the quasars actually differs from our motion with respect to the CMB. That is to say that we are moving differently than all of these things, these redshifted expansion markers are moving with respect to us. This is extremely troubling, actually. So what does that mean? Well, for starters, it contradicts this cosmological principle, and it challenges the assumption that the CMB dipole is simply due to the relative motion, right? And what that really means is that it's probably not fair that we subtracted this stuff out in order to get this picture here. And so that puts us kind of in a world of hurt as with regard to sitting on this CMB as a pillar for, or being an evidence for something that occurred. Now, let me give you some idea of what it's like to propose that you're able to view the echoes of a very distant event. If I took an ice cube and I put it on the table, and I took a movie of it for the next half hour as it melted, and then I kept the movie going for another week, and it evaporated, or I don't know how long it would take to evaporate, maybe only the rest of the day. The proposal that I could look at a picture of all of those water molecules and reconstruct them into an ice cube is essentially what we're saying here about the inception of the universe. That we can look at that glow and reconstruct the ice cube as the result of it. Now, if we can't do it for an ice cube, what are the odds we can do it for everything in existence? It's a very tenuous proposal. Now, all of this is not to say that there wasn't a beginning to the universe. It's only to say that our evidence for it is lacking some believability. Okay, do I want to say anything else about that? You know, this problem, as it's called, so lambda CDM is under extraordinary revision and assault right now. This problem is actually called the axis of evil in cosmology right now. That's their term, not mine, actually, which is quite fascinating. So the standard cosmological model assumes right now that the CMB and our interpretation of it is correct. However, there is this correlation between the plane of our solar system and the rotation of galaxies and certain aspects of the CMB, like its polarization, right? So that means that actually our view of the CMB seems to be affected by our own system's motion itself, which doesn't seem to be correlated with the absolute motion with regard to these redshifts. This is a serious sign that something, that perhaps this CMB means something other than we think that it does. This is all so new, by the way, that it's absolutely forgivable that it hasn't made it into your textbook. This is literally what's being discussed in the astrophysical journals right now. All right, let's keep going. So it does appear that galaxies are organized into groups, which is quite fascinating. So there's these things called clusters. We have our own local cluster here, which you can see. You know, our own Milky Way galaxy is that little dot in the top disk. That top disk is fit into this even bigger disk, which is millions of light years across and contains a number of other little satellites and galaxies. And we can see these clusters all throughout the cosmos when we look around. And we organize them a little bit, right? We can say that, that some galaxies, we call them either rich or poor. Now, small galaxy groups like our own are hard to see at far distances. But the more substantial galaxies are easier to spot. So the richness or poorness really depends on how much of those fully formed galaxies each one of those clusters contains, or how chaotic and undeveloped they are. So the nearest moderately rich cluster to us is called the Virgo cluster, which is, of course, in the constellation Virgo. And extremely rich clusters, like the Coma clusters, usually have a high concentration of galaxies close to the center. And we can see giant elliptical galaxies in these regions, but very, very few spiral galaxies, which is interesting. These spirals usually exist on the outside of the clusters. So we might, your textbook makes the case that ellipticals could be thought of as highly social. They're often found in groups. They hang out with one another. And the spirals, on the other hand, are sort of shy loners. And that's, I think, a fair way to think about them. Come on. Okay. So, you know, we're trying to ask the question of how these things came to look the way that they do. And the short answer of that question at the moment seems to be a combination of dark matter, stuff we don't understand, plus gravity, plus a lot of time, right? And so we've already seen that these more numerous, bluer, clumpier galaxies are way off in the distance. And the question becomes, is this due to time? Is this due to looking at something across gazillions of light years? We don't know. There have been some different galaxy formation models to explain these, but we can basically group them into two bins right now. And I have these illustrated for you right now. So the first model asserts that the massive elliptical galaxies formed in a single rapid collapse of gas and dark matter, during which virtually all the gas was quickly churned into stars, and then afterwards the galaxies sort of decayed a bit, only as the stars evolved. And this is what the astronomers call a top-down scenario. The alternative to that, a bottom-up scenario, suggests that the giant ellipticals were formed mostly through mergers of smaller galaxies that had already converted some of their gas into stars already. So we don't actually, well, astronomers haven't really concluded which one of these models they prefer in terms of the overall metamorphosis of our universe, but these are the two phenotypes we see. And of course, spirals like our own seem to form mostly bottom up, right, through the mergers and so forth over a long period of time, which is much more complex. And here you can see, this is another image from your textbook. This is actually just trying to show how the nuclear bulges can compile. It's essentially showing you that sometimes they happen through the collapse of a single cloud, and in some cases they grow through mergers with other smaller galaxies. Actually, Hubble originally thought that the elliptical galaxies were young and they would turn into spirals, but it turns out that this doesn't seem to be a tenable proposal. It's more likely the other way around, where spirals can crash together and turn into an elliptical, and the ellipticals are actually much more chaotic as a result of that. All right. Now, one thing that's really cool is as we're able to see with greater and greater precision, we can start to see that these clusters also are interacting with one another and strewing out pieces of material in between them. This is another one of those Hubble deep field images. And there's something of a train wreck happening here between a couple of these galaxies in the center. And if we actually zoom out a bit more, we end up with something that's really, really fascinating, which is that these galaxies seem to organize themselves into these giant filaments across the cosmos as well. There's a radial architecture to this, something of a spider web of material throughout the universe, which is very, very fascinating. Well, it's fascinating for a number of reasons, but this is actually probably the strongest evidence, well, yes, it's probably the most accepted and agreed upon difficulty with respect to this cosmological principle, because there's huge voids between some of these filaments, right? There's places where we look where things aren't happening the same as they're happening over here. And, the best attempts to explain this, like I said, are still something around the idea that this process is organized by gravity. However, that gravity is not ascribed to ordinary atoms for some reason. Actually, there's only the amount of cohesive forces necessary to produce these filaments requires something like 95% of the gravitation is due to something other than atoms, which is quite bizarre. And so the estimate is that, well, maybe 30% of this is cold, dark matter, which might have, actually, in my estimation, may have some physical explanation. But then another 68% of it is something we call dark energy, which is even more difficult to detect and unavailable to our reason at this moment. Okay. So, I did it again, I said so. Again, we're moving into a place where we need to put a picture together about what's happening here in the universe. there's clearly a lot of dragons going on. And I think that the key to us understanding the essence of those dragons is going to be to examine the pillars of our standard cosmology. The pillars of our standard cosmology are the redshift relationship with distance and the cosmic microwave background radiation. So next week, when we get together for our last week, sadly, we're going to try to put a bow on this whole project that we've gone through here. And to do that, we're going to, I think that we've done a pretty good job of understanding this redshift business as much as we can say about it, but I think what we'll really have to do now is understand why we think that this microwave signature is from the cosmos and how we arrived at the pictures that we have of it. So on Tuesday, we will tear apart the cosmic microwave background radiation. And then on Thursday, when we close this all down, we're going to examine some potential alternatives to the cosmology that we've embraced for the last 50 or so years. All right, thank you guys. Have a great rest of your week. We'll see you then.